Continuity of polynomial functions. Hello everyone. To begin, let's look back at what we have already covered. In our previous sections, we established the rigorous mathematical definition of continuity, which provides us with a precise way to determine if a function is unbroken at a certain point. To recap that definition, we say that a function, f of x, is continuous at a specific point, c, if the limit of f of x as x approaches c is exactly equal to the function's value at that point, which is f of c essentially, the graph must actually reach the value that the limit predicts. Now that we have this foundational rule in place, we are going to apply it to a specific and very important class of functions. In this subsection, we will be examining polynomial functions to determine if they always satisfy this condition of continuity. Understanding polynomial functions. Now that we have established the rigorous definition of continuity in the previous slide, let us focus specifically on polynomial functions. Before we can discuss their continuity, we must first have a clear understanding of what a polynomial function actually is. Essentially, a polynomial function is a function that can be expressed as a sum of various powers of x, where each term is multiplied by a constant value known as a coefficient. If we look at the general mathematical form on the slide, we represent this as p of x equals a sub nx to the power of n, plus a sub n minus 1x to the power of n minus 1, continuing this pattern down to a sub 1x, and finally adding a constant term, a sub 0. To clarify the components of this formula, the letter n represents the degree of the polynomial, and it must be a non-negative integer. The terms a sub n minus 1, and so on, down to a sub 0, are real numbers which we refer to as the coefficients. Finally, x is our variable. To make this more concrete, let us look at a few common examples. A constant function, such as f of x equals 5, is the simplest type of polynomial. Next, we have linear functions, such as f of x equals 2x plus 3. Moving to a higher degree, we have quadratic functions. For example, f of x equals x squared minus 4x plus 7. And finally, a cubic function would be something like f of x equals x cubed plus 2x squared minus x plus 1. Understanding this structure is crucial, because as we will see in the next slide, these specific characteristics are exactly what allow polynomial functions to be continuous everywhere. Why polynomials are continuous? Now that we have a clear understanding of what polynomial functions are, let's examine why they are always continuous. To do this, we will apply the 3 rigorous criteria for continuity that we introduced at the beginning of this lesson, testing them at any arbitrary real number, which we will call c. First, let's look at step 1, the existence of the function value. If you think about the structure of a polynomial, it is simply a sum of powers of x. This means a polynomial function is defined for every single real number. Unlike rational functions, which we will discuss later, there are no denominators here that could become 0, and there are no square roots of negative numbers to worry about. Therefore, the function value, p of c, always exists. Moving on to step 2, the existence of the limit. For any polynomial, as x approaches c, the value of the function, p of x, simply approaches the value obtained by substituting c into the function. This is a very useful rule known as the direct substitution property. Because of this, the limit of p of x as x approaches c always exists. Finally, we reach step 3, the equality of the limit and the function value. Since we can find the limit through direct substitution, it will always be true that the limit of p of x as x approaches c is exactly equal to the function value, p of c. Because all 3 of these conditions are satisfied for every real number c, we can conclude that every polynomial function is continuous across the entire set of real numbers. This theoretical foundation is crucial, as it explains why the graphs of these functions are smooth and unbroken, which we will see applied to real-world physics trajectories in the next slide. Real-world application, smooth trajectories. Now that we have established the theoretical proof that all polynomial functions are continuous, let us look at how this applies to the real world. In the field of physics, the position of an object moving under constant acceleration, for example, a ball thrown into the air, is modeled using a quadratic polynomial. The formula for this is s of t equals 1/2 gt squared plus v0t plus s0. Since this equation is a polynomial function, we can apply the logic we just discussed to conclude that the function s of t is continuous. To understand this in practical terms, consider the motion of the object. In the physical world, an object cannot simply teleport from one position to another. It must pass through every single intermediate point in space as it moves. Therefore, the unbroken nature of the polynomial graph is not just a mathematical curiosity, but a direct representation of smooth, continuous motion. Having seen the theory and a real-world application, let us now move forward to a step-by-step example to see how to verify this continuity numerically. Step-by-step example. Now that we have discussed the theoretical framework and seen how these functions model real-world motion, let us apply those concepts to a concrete example. We want to verify the continuity of the polynomial function p of x equals 3x squared plus 2x minus 5, specifically at the point where c equals 2. To do this, we will follow the three-step criteria we established earlier. Step 1 is to find the actual value of the function at x equals 2. We do this by substituting 2 into the function for every instance of x. This gives us 3 times 2 squared plus 2 times 2 minus 5. When we calculate this, we get 12 plus 4 minus 5, which equals 11. So the function value, p of 2, is 11. Step 2 is to find the limit of the function as x approaches 2. As we mentioned in our previous discussion on the direct substitution property, for any polynomial, the limit is simply the value obtained by substituting the point into the function. Therefore, the limit of 3x squared plus 2x minus 5 as x approaches 2 is calculated as 3 times 2 squared plus 2 times 2 minus 5, which again gives us 11. Step 3 is to compare these two results. Since the limit of p of x as x approaches 2 is 11, and the function value p of 2 is also 11, the fundamental condition for continuity, that the limit equals the function value, is satisfied. Consequently, we can conclude that the function p of x is continuous at x equals 2. Furthermore, since the number 2 was chosen arbitrarily, this same logic applies to any real number, meaning the function is continuous across the entire set of real numbers. While this process is straightforward for polynomials, it is important to remember that not all functions behave this way. In the next slide, we will look at some common mistakes and distinguish polynomials from other types of functions. Common mistakes. Now that we have walked through a practical example of verifying continuity, let us address some common pitfalls that students often encounter when dealing with these concepts. First, it is very important not to confuse polynomial functions with rational functions. A frequent mistake is assuming that any function containing the variable x is automatically a polynomial. However, a rational function, for instance, f of x equals 1 over x, is actually defined as a ratio of two polynomials. This is a critical distinction because, while we have established that polynomials are continuous everywhere, rational functions are discontinuous at any point where the denominator equals 0. Secondly, I want to caution you against overcomplicating your proofs. Some students attempt to use the highly technical epsilon-delta definition to prove the continuity of a polynomial. While that approach is mathematically rigorous, for the grade 12 curriculum, it is entirely sufficient to rely on the direct substitution property that we applied in our previous step-by-step example. By keeping these 2 points in mind, you can avoid unnecessary errors and keep your analysis efficient. Now, let us move to the final slide to summarize our key takeaways. Key takeaways. To wrap everything up, let's go over the key takeaways from this lesson to ensure you have a solid grasp of the concept. First, as we discussed when looking at the criteria for continuity, a polynomial function is defined for all real numbers x. This means that no matter what value you choose for x, the function will always produce a valid output, as there are no denominators that could lead to division by 0 or square roots of negative numbers. Second, for any polynomial p of x and any real number c, the limit of p of x as x approaches c is always equal to p of c. This is the direct substitution property we applied in our step-by-step example. Essentially, the value the function approaches is exactly the same as the value the function reaches. Finally, we reach our main conclusion. All polynomial functions are continuous on the interval from negative infinity to positive infinity. In simpler terms, because they satisfy all the mathematical requirements for continuity at every single point, their graphs are smooth, unbroken curves across the entire set of real numbers.